In this lecture, we will learn about work done by electric field on charge. What happens when we keep the charge in an electric field? We will also discuss the term of electric potential. In this lecture, we will discuss about work done by electric field, integral form of the work if field is non-uniform, and the behavior of work and field, that is conservative and non-conservative types. Thank you. Whenever we keep the charges in electric field and we want to move the charges in electric field, some work is to be done, some force to be applied. We will discuss the concept of this force and the properties of this force here. As we know that the particles are free to move if positively charged, normally tends towards region of low voltage. While if the particles are negatively charged, they tend to shift towards positive side or higher voltage. However, any movement of a positive charge into a region of high voltage require external work. So try to learn this. The particle, if positively charged, try to move to the negative side, and if it is negative charge, try to move with positive side. But if you want to move a positive charge towards positive direction, then some work against the field is to be done, which is equal to work that electric field do in moving that positive charge in the same distance in opposite direction. Similarly, if require positive external work to transfer a negatively charged particle from region of high voltage to lower voltage. So the basic thing about this is, whenever you want to push or force your charged particle against their own moment, you have to do some work. When a charged particle moves from one position in electric field to another position in the same electric field, the electric field does work on the particle. The work done is conservative. We'll discuss this term later in the lecture, but even whenever we talk about conservative, it means suppose some field is doing some work, moving a particle, and if you move the particle in opposite direction, you will get this work again. This is conserved. It will not dissipate in the form. It will not lost. Hence, we can define a potential energy for the case of force exerted by electric field. This allows us to use the concept of work, energy, and conservation of energy in the analysis of physical process involving charged particles. So this can be done. Yes, we talk about the conservative force. So the potential can be defined, and we can talk about work, energy, conservation, and other involvement of other particles and electric fields. When a charge moves in an electric field, something has to do work to get the charge to move. To move charge, we apply a force to just barely overcome the repulsive force. Suppose you are having suppose you are having one force charge here at this point, right side, and you want to push another charge here, then you have to do some work. That is sure. As we know, the force is always equal to mass into acceleration. So, and work is always defined as force into displacement, and force can also be written as QD. That Q is the charge, E is the electric field. Now, the energy is always equivalent to work, which gives the idea ability to do work. Whether you can work can be done or not will be checked by the energy. When an object has its energy, it has ability to do work. An object has energy by virtue of its position. The field is defined as a region where we observe force, gravity, electricity. So first and the most important thing for this is field. We must have a field. In that field, we talk about movement of charges. For movement, we need force, and if we are moving the charges, then we are talking about work, energy. So we must realize this. A field is said to be conservative if object travel in a closed path, makes a round trip, and doesn't work is done against the force associated with the field. Suppose suppose we have a charge Q, capital Q, and we want to move this small q charge and the charge towards this capital Q. When charge moves towards Q, work is to be done. And that work we use in the form of FD, force into displacement. Finally, we move this. Initially, we have started from point A, the distance is point RA, then we move this to B point, that RB. If the force on here is QE, F is equal to QE, then W can be written as QED. So W gives the idea of work done, that is QED. If the force is uniform, our formula is right. Work is equal to F3. But in a practical case, the field is not uniform. So we have to move to integral form of this. Suppose you worked something to move a charge, but field is not uniform. So for the sake of convenience, suppose you want to move your particle at distance, total distance L, you are moving only up to dl, then we will define it as, suppose you work dw work for a small distance dl and work is dw. dw work is done by applying a force F up to dl, then dw is equal to F dot dl. So total work done is equal to W is equal to dw integral. If you integrate all the work, you will get F dot dl integral 0 to x. In place of F, you can use QE. So this is QEDL. Here we have used minus sign. The minus sign indicates that the work done by the system to move charge from one point to another. If work done by the system, that is minus. If work done on the system, it is plus. So it is just to see you are forcing your particle to move in opposite direction. Yes, when you mind this, then the electric field is the work done on a charged particle by electric field. The equation for electric work is equivalent to that mechanical work. That is why we have calculated electrical work that is equivalent to mechanical work also. So, if the work is done, then you can write this work as Q E dot dr from A to B. Here this E can be done as Fe over Q. If F is force is equal to QE and Q will cancel out, you will FDR. Here we have shown a different way to write this. Q is the charge of the particle, capital Q, and small q is the unit charge where we are trying to move the small q in this field. E is the electric field. Fe is the Coulomb force. The displacement is given by R and we are using dot product. Means skill. Work is skill product. We have discussed how to calculate electric field effect on the charge, means work done. As we have discussed in the previous slides that the electric field is conservative. but this may be asked in the exam. Why? It is conservative because work done by force in moving a particle from one point to another depends only on initial and final points. It does not depend on path. It depends only on A and B, from where you are going and for where you will reach. It doesn't depend from which path you are using. We have done such type of experience work many times. Suppose you want to move from A point to B point by this way. Then this is not matters from where you are moving. You can also move from this. Either you use this or you use this. You can also use this. Whatever path you are taking, the answer will be, work done will be same. Such type of work is called conservative field. These fields are called conservative. Actually, there is no dissipation in this. And all the time, if you reverse it, you will get the work that you have used. That is the reason these type of fields are always conservative in nature. These fields are depends only on initial and final position. If we are talking about conservative nature of electric field, this means then the line integral of electric field along a closed path is 0. The line integral will give you 0 answer. This is the mathematical side of this conservativeness. Consider 2 points A and B in electric field due to charge Q. And suppose you are moving a particle test charge from point to your charge Q field Q. We have to add work, and suppose you are using infinite changes, meaning small changes, then you can use integral form of this. This is called line integral. If you are integrating about a line, and these two ways, whether you are using the first way or second way, the answer will be same. This doesn't depend on path followed. It depends only on initial and final position. A and B will be independent of path followed. So we say the electric field is conservative in nature. We can calculate the field also. Suppose you want to move from A to B, as we have discussed in the. Suppose you want to move from A to B by some way. You want, this is your A point, and on the other side you are having B point. You want to you go from A to B, then this will be your work. A to B is equal to E dot dl, line integral. If you want to move from B to A, the line integral will be B to A this. And the total closed path line integral will be A to B, B to A. But we know that A to B EDL is equal to B to A minus EDL. If you put this value here, you will get 0. So the answer is conservative. If the fields are conservative, then only on reversing the answer is same, work is same. If it is same, the total in cyclic path total work is 0. There is another kind of fields that is called non-conservative fields. To be non-conservative fields, there must be a mechanism to convert energy to another form. Since even non-conservative fields must conserve energy as a whole with dissipated energy, thus a non-static field can radiate away energy or dissipate it as heat in eddy current in conductors. In non-conservative fields, we always have some losses, energy losses. The most common way of energy dissipation is in the form either in the form of heat or friction or eddy currents or magnetic electricities, which starts the type of field called non-conservative fields. Thank you. In this lecture, we have studied the effect of field on charged particles, conservative and non-conservative fields, and integral form of work done.